Climate change is a daily media conversation, and I think that most of us in entertainment lighting are now firmly signed up to the fact that we need to do as much as possible to help the environmental cause. Today, we want to ask the question, what decisions can we make to reduce climate change in entertainment lighting? We must consider that every purchase has a consequence. So just how do you make an educated decision? After all, it's all of us that are responsible. So, with more information, will the decisions we make be different? We're going to talk about the carbon footprint of a product, and we'll use carbon dioxide released into the atmosphere in grams, kilos, and tons as a measurement. So here's some context to help illustrate the points. According to the Climate Neutral Group website, a metric ton of CO2 is equivalent to an average petrol car travelling around the Netherlands for just under 10,000 kilometres, or an electric car for just over 11,000. It's 72 trips between Amsterdam and Paris on the train, or 2.6 economy flights between Amsterdam and Rome. It volumes out to be equivalent to 500 CO2 fire extinguishers, and it will take 50 trees to grow for 1 year to capture this carbon. Now, obviously, this is a very general comparison. There are many assumptions and caveats. So, if anyone wants to see more detail, you can check this out on the Climate Neutral Group's website. We're going to look at the 4 stages of a product life cycle: manufacturing, distribution, usage, and end of life. This presentation comes with some caveats. As an industry, we have a long way to go when it comes to collecting data that will allow us to truly assess our carbon footprint. Therefore, the numbers that we use today will be indicative and serve to demonstrate the points made about the environmental impact of product. Let's start with stage 1, manufacturing. This is by far the most complex issue. We're frequently asked questions like, how much embodied carbon is in your product? But what does that even mean? Well, very simply, embodied carbon is the carbon footprint of a product when it rolls off the manufacturing line. For us to establish the embodied carbon number, we would first need to understand how much carbon is produced in each of the components that make the product. We would need to understand the volume, weight, distance travelled, and energy used in the manufacturing process. But that's not all. These components are generally made from raw materials, which typically have their own journey. Think about a semiconductor or a glass lens. The location where they're constructed is not the start of their carbon journey. The journey started as soon as the minerals were mined. I think you get the point, right? It's complex. Generally, materials are moved to component manufacturing locations. Components are made, then either moved to assembly locations, or, as is often the case in our industry, they're moved to locations where sub-assemblies are made and then to a final assembly point. Take Source 4 LED as an example. This product utilizes over 1,400 components, which are sourced from 17 countries around the world. Also, consider that this is a fairly efficient product to build, as we do not bring in sub-assemblies. We manufacture from component level ourselves in the US, and the component mass volumes out to be quite small, certainly when compared to automated lighting, which can have upwards of 3 times the mass and 3 times the component count. At this point, I just want to draw some comparative data from other industries. Research carried out in the US suggests a typical smartphone has 55 kilograms of embodied carbon, and a Surface laptop has 119. We believe this range could be indicative to that of a generic LED luminaire in our industry. A retrofit LED engine might be at the lower end, and a complete ellipsoidal at the upper end. Obviously, these are very rough comparisons, designed to give you an idea in terms of order of magnitude. But let's remember these figures, as we'll refer back to them later when we build up a picture of the overall carbon footprint of a product. It sounds obvious, but it's worth remembering. If it's complex and heavy, it's likely to have a large carbon footprint out of the box. If it's simple and light, that carbon footprint will likely be smaller. So it's really important to think about what you need. Retrofit LED upgrades can be a good low-carbon option if you already have a tungsten fixture. They'll save you money too. Now let's move on to stage 2, distribution. Whilst it sounds straightforward, the choices you make could significantly increase or decrease the carbon footprint of your product. There are 4 traditional methods for moving goods around the world: sea, air, road, and rail. Sea and rail freight produce a similar amount of carbon, roughly 15 grams per tonne per kilometre. Road freight is slightly higher at just over 60 grams, and air freight comes in at a whopping 540 grams. Now let's take our Source 4 LED. This fixture weighs 8.9 kilos. If you're a buyer in London, your Source 4 will need to travel just over 1,600 kilometres by road and just under 6,000 kilometres by sea, giving the product 1.4 kilos of carbon. If we decided to air freight, it would increase the produced carbon number to 30.3 kilos, costing the environment 19 times more. But why would a company like ETC use air when we could use sea? Well, the truth is we don't want to. It's expensive for us and it's expensive for the planet. To counter this, we invest in local stocking facilities and we fill them with stock. This gives us stock to service local customers whilst we replenish using sea freight. Whilst this helps, it does not alleviate the problem. We still have situations where clients want product quickly and our local stock has run out. Another area for development in our industry is localized manufacturing and short supply chain. We've recently started a program with sensor power control modules and source forwards. If you're a customer in Europe or the Middle East and you buy a source forward or sensor module, it will come from our manufacturing facility in Ede, the Netherlands. This cuts down the carbon footprint and speeds up delivery times. Our industry has lots of room for improvement when it comes to moving product. But my advice is to find out where your product is coming from and how it's getting to you. Where possible, try to avoid air freight. Now that we have our fixture, we can look at stage 3, usage. Energy usage is a big fish in the carbon footprint of an entertainment lighting product. And there is a lot that we can do and have been doing in this area. If we step back in time to the 1980s and before, theatres were lit with 1.2 and 2 kilowatt luminaires. In 1991, the Source 4 was released and it produced the same amount of light for half the energy. Then, around 10 years ago, the Source 4 turned LED and reduced that energy usage by a further 75%. This is a massive improvement, especially when you consider the saving does not just materialize in the energy used for powering the luminaire. The venue will also require much less cooling. So there's another saving there too. Moving lights have not progressed as well, in my opinion. Even LED lights use quite power-hungry engines, ranging from about 280 to over 1 kilowatt. There's a reason for this. Firstly, they have a condensed optical system. Most push light through a small gobo gate and multiple lenses. This is done in order to make moving lights compact and feature-rich. It does have its upsides. You can certainly argue that because a moving light can do so much more than a generic, it has a large offset. I think this is true, as long as your moving light is replacing the work of multiple generics or doing something that a generic cannot do. However, if you have a moving light that is acting as a generic, it is, of course, costing the planet more. So how much carbon are these fixtures producing? Well, to answer that question, we're going to have to dive back into the maths. Let's look at a lineup of generic fixtures. At the top, we have our typical usage. We have gone for 3 hours a day, 6 days a week, and 50 weeks a year. This is just our assessment of typical usage. Here, in the top right, we can see how much carbon the UK produces for each kilowatt hour of electricity it delivers. In the left column, we can see the fixtures. Next, their associated power consumption, and then power usage in a year based on typical usage figures. Then we can see how much CO2 that fixture produces in a year. You can see the drop-off when you get to LED fixtures, which is great news. But this is not really a fair assessment, as the fixtures are outputting different brightnesses. Now let's reveal the lumen output of each fixture. If we take that lumen output number and divide it by the power draw, we get lumens per watt, which reveals the true efficiency of the fixture. When thinking about LED in comparison to tungsten, there's more you need to consider. This information here demonstrates the worst case scenario for LED, and that's because we're making white light, which is when they're at their least efficient. As soon as you start mixing color, the additive color mixing system of the LED is becoming more efficient because we're turning LEDs off, whereas the subtractive color system in tungsten is becoming less efficient, as the gel color only lets a certain amount of light through. To demonstrate this, we're going to compare Source 4 Series 2 LED and Source 4 tungsten. We'll have both fixtures produce half CT blue, and we'll adjust the intensity to be level with the weakest fixture, which in this case is the tungsten. By doing this, we can see that the tungsten uses 750 watts, but the Series 2 only uses 111 watts. Series 2 is using 85% less power in this scenario. ETC work very hard on the optical efficiency of fixtures. Whilst I'd like to say this is to reduce the product's carbon footprint, there are other considerations in play. One of those is reduced heat gain output, which allows the cooling fans to run slower and the LEDs to last longer. The benefits of this are that you have a much quieter fixture, which is still able to operate at a high intensity level. And I'm not talking about silent mode, which reduces the output. We genuinely just don't need as much cooling. And if the LEDs are not running as hot, they'll last longer, thus giving the fixture a longer lifespan, which is one of the reasons we feel confident giving the LED engine in our fixtures a 10-year warranty, and the fixtures have passed the LM84 test process. As we move on to stage 4, I want to come back to the carbon number that the fixtures produce in a year and compare to the embodied carbon number from earlier. When we consider that comparison, it is likely that the building of a fixture is comparative to 2 to 3 years of fixture usage. This brings the environmental importance of fixture longevity into stark contrast. In recent years, there's been a consumer boom in low-cost manufacturing, and in some cases, the old adage of, if you buy cheap, you buy twice, has been deemed acceptable. I'm sure we've all heard comments like, it's fine if it doesn't last that long, it's good enough and cheap enough to replace. Well, fiscally, that argument may stack up. Environmentally, it does not. For fixtures to last, they need to be well-designed, well-built, well-supported, and parts need to be readily available, even for a sustained period after the fixture is discontinued or superseded. Doing this costs manufacturers money. It's a big commitment, but ultimately, the planet needs manufacturers to do it. So let's look at the carbon footprint of a Source 4 Series 2 luminaire over a 10-year period. If we use the embodied carbon number from a Surface laptop as a reference, we would have 119 kilos of carbon embodied in the manufacturing process. If we use efficient transport, we can expect to add another 1.4 kilos. If we keep the luminaire for 10 years, we would add another 350 kilograms of carbon from fixture usage. So over a 10-year period, we will have added 470 kilograms of carbon to the atmosphere, or 47 kilos per year. Now let's run those numbers again, but this time we'll make different choices. We'll choose a product that uses 25% more power and has a likely usable lifespan of 5 years instead of 10. We'll also suppose that the product is delivered by air freight. We'll use the same embodied carbon number of 119 kilos. However, we'll need to add it twice, as the product's lifespan is 50% shorter. We'll also add air freight twice and an increase in energy usage of 25% over the 10-year period. Doing it this way, the fixture is going to cost the planet 700 kilograms in carbon. It's a big difference. If we take this and we extrapolate to a typical small to medium theatre using, say, 60 luminaires, the latter example is pushing an additional 14 tonnes of carbon into the atmosphere over the 10-year period. Little choices make big differences. It's also worth noting that retrofit LED options would further reduce the carbon output. Obviously, there are some assumptions in these numbers. They're not designed to give you an accurately scientific portrayal of carbon emissions. They're to illustrate some key points. So my summary is this. Whatever you buy, stop and ask yourself whether the decisions you're making are right for the environment. If you need a moving light for its features, then use a moving light. If you're considering specifying a moving light because you just don't have time to figure out how the product's going to be used, stop and spend some time figuring out what you're going to do. Buy a product that will last. This just makes good sense, not just from a carbon emissions point of view, but also from the waste disposal aspect too. Also look at how efficient the fixture is. Make sure it's making nice light at the stated efficiency and calculate your lumen per watt. And please, where possible, try to avoid air freight. Finally, I'd say this. Push us, the manufacturers, to do more. As an industry, we can improve, and I'm sure we will. But we'll do it faster if customers keep telling us we have to.